Uh, yeah, Austin asked how many watts can we get out of this? There's a lot of science out there. Um, this is well, welcome back. Since Austin is here and he asked the question, I'm just going to go ahead and start, and the rest of you may or may not be interested, but basically you have a moving, with the idea of a piezoelectric is you have a moving object, and that object deflects a piezoelectric material which produces a charge, and that charge is related to voltage because of the material. And this, okay, where'd it go? This one? No, yeah, that one. Here's a table. When I upload the newer version of the PowerPoint, you'll see a link to this. But this is called. Let me do this table first because this is actually answers this question. Microwatts and milliwatts is the answer to short answer to his question. Not a lot of power is the specific answer, but obviously it has to depend on the size of the material and the power, mechanical power going in to move it. There's a bunch of cool pictures in here. This is like page 24. It's a 63-page review article, but it's got a bunch of cool pictures on what these things actually look like. Yeah. Interestingly enough, I think this Zhang down here is the guy who used to be a professor at BME, moved to Dartmouth. And this is the guy who I spoke with down in San Antonio doing experiments. You know, we happened to be there the same day a couple of times. And I got to watch his students try to, but there's a bunch of cool pictures on what these things look like. You know, basically there is a deflector. And mechanically it causes the piezoelectric to move. So yeah, small size, small power, I guess is the answer to the answer. It's not like solar or windmill or nuclear, although, all right. So the answer is microwatts to milliwatts. So we're in the middle of talking about running without a battery or running with a battery. And I'm going to leave this whole topic until we get to a whole chapter or a whole section on RFID and near field communication. Suffice it to say, you've got two coils, and you're going to align the two coils, and energy is going to go from one to the other via you know, the mutual inductance between the two coils. There's a bunch of products out here that fit into this category, you know, that you can purchase. And I get my act together, and there'll be one of the Lab 4 options will be this. I just haven't configured it right. And it has this cool thing with diodes and capacitors. And there's a bunch of different types of circuits that go in here. But basically, double the voltage and half the current. Okay. Okay, so now we're going to go. So we went away from harvesting, and the next section here is storage. And it's basically a review of batteries or comparing batteries to supercaps. And the any questions on harvesting? At least from I know very little, other than the fact that it was the way to solve this medical implant. Batteries were way too big. So obviously all the normal things you might think about choosing a battery. How big is it? Storage is at either in joules or in, this is either in joules or amp hours. That's what they mean by storage. How much energy can it storage up? Although they, as I pointed out, they sometimes use amp hours as in energy units. You know that I don't know, you guys are probably some of you are old enough to remember cell phones, you used to be able to change the battery, right? And batteries would run out and you can just open up the case and put in a new one. A lot of devices, they've decided, I guess for either good reasons or bad reasons, to completely hide the battery and realize it's just better to replace the whole thing when the battery dies. Okay, so weight was a big thing for our rats. Weight's a big thing for soldiers. Weight's a big thing for flight. For space flight or airplane, drone flight. The number of recharge cycles determines how long it will last. And we'll see that voltage is not constant with time, nor is it constant with current. Okay. Now, some of these things have thermal effects. You draw a lot of current out of them. They get very hot. And so you'll see a lot of lithium-ion batteries with thermistors in it, just so to keep it from exploding, right? Because nobody wants the airplane to go down with a fire. And I already told you that lithium fires are very hard to put out. Yeah, where's my thing here? Does anybody know how to put out a lithium fire?
Smother it?
Yeah, with what?
CO2?
Sand?
Sand.
Not water.
Not water, not CO2. I don't think it's not a 1, 2, or a 3, right? So you don't get out a 1, 2, 3 fire extinguisher. I think you dump it in sand. Or in our case, you let it burn down to nothing. It went out on its own. But
So
left a
in
big
solar
hole.
car, we had
What?
in solar car we had battery packs that were like 400 lithium-ion batteries, and if they ever caught, you just let it burn for like 6 hours.
Well, unless you had a lot of sand, I guess.
Yeah, we had a couple buckets.
We burned a hole right through a table in the old building, and like I said, there's a lot of paperwork. Basically, I charged this with one of these batteries actually, and I didn't use the right charger, or I set the charger to 7.4 volts rather than 3.7. Luckily, it wasn't in the rat at the time. This is what I mean by we gave you the down here in the blue with an equal signs was the battery, the budget, the budget equation. It's not true. It turns out that given a certain battery, depending on how much current you draw out of it, the lifetime, in this case, the available capacity changes. Okay, and so if n were up here in this equation, if n were equal to 1, then this would be the energy budget equation we did at the beginning of this. Okay. For reasons that I don't know, the author switched the parameter from E, or I switched it. I don't know, somebody switched it to C, but they're the same thing. This is in amp hours. This is in amps, and that's in hours. And N is not 1, and it depends upon the battery, and obviously the amount of capacity. So when you choose a battery, you obviously choose one that is rated for whatever delivery you want to generate. Obviously, it's a pretty big battery. That's a 100 amp hour battery. Those are big batteries. Okay, and that's called a Perkett curve. This is the other thing you probably know about batteries, and that is with primary batteries and nickel cadmium batteries and nickel metal hydride batteries. You could measure the voltage, and since it's a monotonic, if you look at voltage versus capacity of a nickel metal hydride, you do see a monotonic curve. And so you could, this is the same way the primary battery does this as well. You could measure the voltage and calculate the capacity. But for lead acid batteries and lithium ion batteries, it's, you know, a 3.7 volt battery is whatever, 4 volts when you charge it up, but it remains pretty close to 3.7 until it has no more life, and then it drops like a rock. Okay. So in that regard, you can't look at the voltage of a lithium ion battery and determine its capacity. So there's a poll the audience question. How do you measure capacity, right? How much, you know, this number down here, the percent capacity discharged, how do you measure capacity of a lithium ion battery?
For solar car, we had that we'd measure the current going out, and we kind of do like a integrate the power over time sort of thing.
Yep, that's what they do. And so you know how much you know what this total should be, right? Because you've tested it. All right, so now here's an easy question. How do you measure I? And a hint, that's a slide about 10 back.
Your special current amplifier.
Yeah, your current sense amplifier. So things where you do have a lithium ion battery embedded in the product and you wish to know its capacity, right? So you can warn the user or somehow go into low power mode or whatever, you're going to put one of these current sense amplifiers in your product. Measure current as a function of time, integrate it, obviously, and determine capacity that way. Now, you got a cheaper way to do it?
Guess.
Yeah, well, how do you guess? Yeah, sure, guessing is not bad.
It's just cheap.
No cheating.
Well, measuring the voltage and then trying, if you have
No,
this.
that doesn't work. The voltage is not your help, not your friend. It's and the trouble is it's not the same. It's not repeatable. Voltage doesn't give you any hint. I want the same equation. I'm just going to rewrite it. What is this equation? What's this? Hey, there's some easy calculus for you. What's that? All I did was assume that current was constant.
0 T to dt is time.
Just time, yeah, it's just T. Okay. So if I just measured how long it was running over how long it normally runs until the battery goes down, that's a simple approximation for capacity. All right. I've seen this plot in different units or different. I wouldn't make a lot of stock in the actual numbers of this plot, except that to know that you have rechargeable batteries, secondary batteries, and lithium ion is better than nickel metal hydride. Nickel hydride is better than lead acid if you're looking for power density. Okay, power density obviously is the ratio of power to weight. And then in the same way, they're also better for energy density, which is power, which is energy in joules well, or something like joules per weight. And so if you were to make a general statement between lithium ion batteries and supercaps, right, you could say that the supercaps are not necessarily better for energy density, but they're better for power density. So supercaps are appropriate for high power applications, whereas lithium-ion batteries, at least with the current technology, better for low power, low weight applications. Okay, let me see energy density. Yeah, so there are a couple of types of supercaps. Yeah, we harvested these out of a Dell server. You know, so they used it for, you know, basically a short amount of time, a short time battery backup. So if power goes out, the server could continue to run, and they can be big. Okay. So again, here's a comparison between lithium ion and supercaps. Obviously, it's right out of the book, right, Tom? Right out of the book. I just retyped it. So, you know, in terms of energy storage, the lithium ion is better. It's lower weight per joule, but in terms of current, the supercap is good. This is what causes your cell phone to die, right? That's exactly how many days your cell phone will last. Somewhere between 100 and 1,000.
How well is the technology for supercaps?
I have no idea. I mean, when I went to buy them a couple of months ago, there were a lot of choices.
Yeah, I mean, just like 10 years ago, this wasn't a very common
No,
thing.
no, I think it's you know, again, it's not my area, so I don't know. Obviously, if you're talking about putting in a battery in an IoT device, dumping it in the bushes, right? Or say you have a you know, a solar panel that runs during the day, charges up a lithium ion battery, and it runs at night. If you're thinking about the kind of IoT device that's in this class, you don't need watts, right? You need milliwatts, and weight is a big deal. No, I think this whole thing is changing, right? I mean, I think the whole point is we're not done with inventing ways to store energy. And the takeaway from this plot isn't any of the numbers. It's this column, okay? This is the column you want to take away. And that is, you know, what voltage does it run at? What temperatures does it run out? How fast can you charge it, right? Look at these bad boys can charge in milliseconds. You can dump a lot of the coulombs. That C is coulombs here. And you already know what happens if you dump a lot of coulombs into a lithium ion battery, it explodes. And so if you need a fast charge discharge cycle, this supercaps where that is good. Yeah, nobody likes to have to replace your cell phone, right? And so yeah, and they're more expensive per watt, okay, per energy or per kilowatt hour. We're more expensive. But okay, so that's enough of that. Okay, so again, where we are currently, and we said you can measure the voltage on a supercap and determine its capacity, right? Because it does drop either exponentially or linearly, as we saw in the previous slide. Okay, so you can look at a. Now, an interesting question is: do I need a regulator for a 3.7 volt lithium ion battery? Maybe yes, maybe no. The advantage of not having a regulator is you're not wasting any power. The disadvantage, your circuits really have to run at a range from 4 volts down to 2 point whatever. If you want to use this whole thing, your system has to run from 4 volts down to 2.7 volts. And there are a lot of microcontrollers that will operate. Unfortunately, a lot of them will also have a speed dependence on the voltage. We ran MSP 430s right off the lithium-ion battery, and turns out it didn't like that. It had to get, it had to go down to 3.8 volts before this guy would not explode. But it more or less ran in a situation almost identical from 3.8 down to 2.7. But a lot of electronics behaves in a weird and unpredictable way as you change its power line voltage from one end of the curve to the other. So you add a regulator.
Are you going to cover different types of regulators like
Yeah, right now, right here, just not in a lot of detail. Not in a lot of detail. I'm going to guess like 2 slides here. Linear regulators have what's called a dropout voltage, which is basically the difference between the input and the output. Basically what it says is the input voltage has to be greater than the output voltage plus some constant. That's a better way to see it. For it to be in operation. They have the advantage of there's pretty easy circuits. Most of them have a capacitor on the output. If you hook up the input to a battery, what's the model of a battery? The battery is essentially a huge capacitor. And so if this is a battery powered linear regulator, the input capacitor could sometimes be skipped. But the output capacitor will stabilize this, from a 20,000 foot perspective. What is this circuit? What shape, what architecture is this circuit? I guess you have to know what an op amp is. What you got to do is you got to draw arrows on all these lines. Okay, you with me?
You get that it's a feedback loop?
It's a feedback loop. Yeah, what direct, you see the arrow? Going that way, okay? When you have a block diagram with an arrow, this is going that way. This is information flow, if you'd like. So in this case here, all the arrows but one are either going down or to the right, okay? This one is a left arrow creating the negative feedback, by the way. The negative feedback because it's going into the minus terminal. So this is a control system, a linear control system. But basically the voltage is dropped across this resistive element in such a way that the output voltage goes to some constant, okay? And that constant is determined by this voltage reference in these 2 resistors.
Are linear voltage regulators the ones where VN has to be larger than Vout?
Yes, yes. That's what, so the question is, are linear regulators the ones where the input voltage has to be larger than the output voltage? And the answer is yes. And that equation is around the term, V, this is a positive number. Okay, so I guess you have to know that V, the dropout voltage must be positive, right? And it's on the order of, some of these, it's like a half a volt. Some of them might be 3 volts. Some of them might be a tenth of a volt. depending upon which one you choose. But the input voltage has to be larger than the output voltage. Okay. If you sort of ignored for a moment the feedback loop and just modeled and somehow modeled this thing here, right? Just modeled that resistor. And this is the input voltage, and that's the output voltage. What general statement can you tell me about V in, V out, I in, and I out?
I in is going to equal I out.
I in, the output current is equal to the input current. Now, it's not perfectly correct, but it's approximately correct that the output current equals the input current. And what was already mentioned, what can you tell me about the two voltages?
The out's going to be less.
Yeah, it's going to be less. All right. So these guys are equal. The currents are equal in the input voltages. And then you can sort of see that from this block diagram. They're also very low noise.
Is that what the capacitors are for? They're there to smooth it out?
Yep. Because it is a controller, right? And so I don't know if you've taken a control system class, but it can become unstable, right? The controller can become unstable, and the capacitors are there to make this feedback loop stabilize. Okay, so it doesn't oscillate. That's what the two capacitors to stabilize them. So often, if they spec 0.1, you can use any capacitor larger than 0.1. And just like most, well, not like most capacitors, these capacitors, like good design, typically show up from a layout standpoint right next to the voltage. I mean, often these chips have desired or recommended layouts for the positioning of these capacitors. But it's low noise, it's low complexity, it's low cost, it's low everything except efficiency, right? Because if this is 25 volts and that's 5 volts, you're dropping a lot of power. So these things get hot. Because the input power, right? If you think about the input power is going to be dropped into the regulator power plus the output power. And because of this, right, all the currents are the same. And so you can calculate essentially the regulator power as V out. Okay, V out, V in, sorry, minus V out over I in, or times I in, sorry. Okay, which is the same as I out. So this voltage difference here, V in minus V out times that current is the amount of thermal watts that this thing is going to dissipate. That's the loss, if you like. And that loss is going to be a thermal. That's an easy one. And then again, I did not intend on, this is actually something I've done a lot of. I did not intend on spending a lot of time on this, except there are 3 types of switching regulators, and their goal is to recover that wasted power, either by allowing the battery to run longer or by making it less hot. Okay. And there's a couple of sort of generalities in this class of regulators. There's usually an inductor. Okay, so there's an inductor. And there's usually a frequency. This thing will oscillate. So obviously there's a, and the frequency is the rate in which these switches here are toggled. right? So it's going to toggle these switches at a rate specified by the switching regulator rate in order to capture all the power. Now, this is, again, a very general equation. Obviously, the output power is probably some sort of, they're rated by efficiency times the input power. So TPS 6301. I don't know, 90%. I don't remember.
Sounds reasonable.
Yeah, I think that's a typical 96%. Okay, now it's up to, they're lying. You got to look and see how you're actually being used. But having a efficiency in the 90% range, which tells you again how much. So if I give you a 96% regulator, right, then the lost power, right? So the power loss here would be 4% of the input power, okay? And the output power would be 96% of the input power. That's what they mean by efficiency. But basically you've got a, you're pumping charge onto this capacitor through the inductor, and the diode is used to cause the voltages to either accumulate, as in a boost converter, or go down. So a buck converter. If you think about a buck converter, think about cowboy. What happens with a man or a woman on a buck and bronco?
They have 8 seconds to stay on, or they.
Yeah. What happens at 9 seconds?
They go flying.
They go flying, but where do they land?
Lower than they were previously.
Lower than. Okay, so V out is less than V in. All right, so if we have a situation where we're dropping the voltage, but we want to be efficient, we'll use a buck, okay? And so, what do you suppose the boost is? What's the word boost mean?
The out's going to be bigger.
Yeah, it gets bigger. So you could use a 1.5 volt battery and boost it up to 3.3 volts. I mean, that's a typical usage of a boost regulator. Use boost regulators if you need some sort of 48 volt system and you don't want to have a 48 volt battery, you can boost it. And buck boost, what do you suppose that means? Either, yeah. So either up or down. And you don't. Yeah.
This might be my lack of circuits acumen, but in this case, what is the diode going to do when it has a reverse voltage on it?
Off.
It's just going to be off. It's not going to.
Yeah. So, for instance, let's say this is 3.7, and this is 5 volts. Okay.
Fine with that.
Okay, that's a boost, right? This voltage will go above 5.
Yeah.
Because of the inductor, right? You're switching it through an inductor. You'll get a temporarily large voltage as you open or close. I forget which one. Probably when you open it, you get a large voltage right here, and that will dump current through the diode onto the capacitor. Now, just like all the other ones, there's a feedback loop in here, adjusting the duty cycle, if you'd like, of this switch. Now it's a constant frequency variable duty cycle switch in order to produce 5 volts out. So once this hits 5 volts, it won't go less than 5 volts because it'll it'll go less than 5 volts as it dumps current in this direction. But it can't dump current in that. Current can only go this way through the switch.
Yeah, I think that makes sense to me.
Yeah, so you're
On
sort of
the-
like a pump, an air pump,
Yeah.
right? With a one-way mechanical valve. I'm trying to
Okay.
blow up a balloon, and you know, or you know, like a hot air balloon where you've got the gas going in. Okay, the heat can go in, but it can't come out.
Yeah.
And so that one makes most sense to me. The buck one. The buck one is it's obviously going to produce a voltage less than. So this again is say 5 volts, and this is the 3.3.
When I used these in the past, the inductor was actually like it had different number of turns on the input and output, so it was actually boosting the voltage. It was for a 9 volt.
It's an inductor. It's not a transformer. There's no
It
input.
was a transformer when I.
Okay, well, I'm not saying there's only. I'm not saying there's one way to do it. Okay, okay. Let's just go back over here. I'm just saying this. Okay, I'm going to see it. This is not a 4-terminal device. It's a 2-terminal device. And it's yeah, it's not small necessarily, because it has to all the current that you're going to regulate has to go through that inductor. Yeah, like this one's got a fixed output, and as you might imagine, it does have a feedback loop. Shown here, shown with the FB. So I'm not saying there aren't dozens of ways to do it, but this one I do believe is this is I forget which kind this is. This is a buck boost, so this has both types. I don't know if they show you how it works or not. They may not show you how it works. Yes, I don't know if that's enough to figure out how the freaking thing works or not. You got to find the diodes. Yeah, I don't see the diodes in here, so I don't think I can necessarily figure how this thing works. Or maybe the diodes are built into the MOSFETs.
Yeah, I was wondering.
Behavior of the
Transformers
diode.
instead.
Yeah, this is not my. I buy them and I solder them down. These are real layout. These are real. These are. Yeah, I'm glad you made me look at it. Yeah, these they really do work at showing you exactly how to lay it out, because these things are really noisy. Again, this thing is oscillating at a particular frequency. It probably said so up here in the specifications. What frequency it oscillates at. Frequency, synchronization frequency. Yeah, at a megahertz about. So, and, okay. So again, I don't know. I'm not saying that regulators never had transformers, but these switching regulators, these are inductors. And there's a really complicated guide for choosing the inductor. Okay, inductor application. Whatever. There's a complicated guide for choosing that inductor. You can't just choose any inductor. Yeah, see, it's showing you how to choose the It's showing you how to choose the value, but there will be a guide for choosing the inductor. Yeah, no, that's not it. Maybe not in this one. And they're tough to solder down too, as you can see, because that, you know, you gotta get that pad soldered down. They will come with a recommended. It will come with a recommended inductor to put on there. Well, it's not this. Yeah, fine.
I posted in chat the chip I use.
Okay, cool. Yeah. Yeah, and it's not, yeah, again, I don't have any, yeah, so, current. They can do you can do large currents. As a matter of fact, it's the go-to guy if they're, oh, it does use it, that is a transformer. I see, all right, fair enough. Fair enough, that's a transformer. Yeah. Oh, 300 volts. I got it. I got it. All right. Now I get it.
Yeah.
It's possible that if you need 300 volts, you got to use a completely different architecture. Yeah. Yep. That, you know, those of you that have old cameras with a flash on it know that it makes a sound. The flash circuit makes a sound. That's this thing oscillating, and it's probably, do you know what frequency? Yeah, 300 kilohertz. All right, I get it. No, those are inductors, clearly. Yeah, this is not meant for 300 volts. These are typically in the 0 to 25 volts range. All right. Now there's chargers, and way back before the lithium ion batteries we had for the 445M robot, we used nickel metal hydride. I've used nickel metal hydride around students because they're less, well, they were cheaper to buy, and I wasn't caring about the weight, but they're also cheaper to charge. And so you can actually trickle charge a nickel metal hydride, just to have some sort of, you just buy yourself an AC adapter that has a current limit of 100, 50 milliamps or so, and just hook it up to the battery. You can trickle charge it. This is an actual charger. I built this circuit. You can, over here, you connect up these in a certain pattern, depending on how many cells you have. All right, 1.2, whatever the, whatever, 4.8, depending on the number of cells you have. I think this is 6 cells.
With the trickle charger, I mean, you just leave it hooked up and it
trickles.
So the load goes up.
Yeah, this is just an AC adapter. So for this particular one, for instance, for this 8.5, we choose a 9 volt, 100 milliamp AC adapter. And you could either plug it in or not plug it in. If it's plugged in, you've got, the 8.4 volt battery connected. It never went larger than 9 volts or 9.2 volts when it's connected, but it's current limited by the wall wart. It took a long time to charge, right? It took whatever, 12 hours to charge it. Whereas something like this can jump a lot of Q and a lot of charge in this very quickly. This is a fast charger, and that's a slow charger. But the whole point is it's really simple. to use a nickel metal hydride, and it's fairly safe as long as you don't hook it up to 120 volts directly or short the output. That's the other thing that can happen to make any battery go crazy, short its output. And then, you know, there's, again, you can do this is a Google search of lithium ion charger batteries. Now you have to have a charger. And so you can't trickle charge a lithium ion battery. It'll get crazy. The chargers are voltage dependent, obviously, and some of the more expensive chargers will sense what voltage the battery is and adjust the output to match. But if it's a good battery charger, okay, what is this?
Temperature measurement.
Yeah, and if it's a good battery, that temperature measurement is embedded in the battery itself. Okay. Now, if it's a bad charger, then there's some sort of thing you tape onto the outside. But if you want a safe operation, you buy a battery with a temperature probe embedded in there, hook it up to your charger so that it will shut down if it gets too hot. Okay. Yeah, there's a reason they don't let you put lithium ion batteries in your luggage and let them bang around. As these things can get hot if they're shorted. And this whole thing is how many coulombs per second can I dump into the battery? Okay, and so they're not all the same. And then there's, you know, you can buy these as obviously as systems, but you can also buy them as reference designs. Okay, what are these for?
Indicators.
Yeah, that's, you know, because there's a human in the loop here probably to let you know when the battery's charged, when it is charging, and when it's, you know, this is probably a red light to say you're charging, and that's probably a green light that says you're done, right? Some kind of thing. All right. Okay, so now we're finally done with 445L, and we're going to go on to chapter 4 in the book. Okay. Don't save. I don't know.
Is the test just covering 1 through 3?
Let me write it. Okay, so when we find, great question. Okay, thought about that about a month ago. I hope the test wasn't today, right? Because I missed it if it was. Okay. Ooh, it's coming up close. Yeah, so that's the answer to your question, yes. So we're switching between exam 1 and exam 2, okay? And, you know, I'm probably more likely to ask you questions on fundamental theories than on detailed circuit design. So if your circuit designs are poor, it's going to be, it'll be on Zoom, I think, or if I can figure out Gradescope, I'll do it in Gradescope. But give me something, you know, good. So I plenty of. So let me create you a study guide. How's that? Right. I'm what? How many days out? Okay, I'm 12 days out. Right. Let me get you a study guide. I'm not the kind of professor who likes to make things hard on their kids. All right. So, thanks for bringing it up, Austin. gives me plenty of time to get it right. And so there will be a couple of sections here in chapter 4. The first has to do with distance. Okay, so and then the second will be communication theory math, information theory. So this is about how distance relates to wireless. Okay, and so we're going to see a couple of equations that relate the signal strength as a function of distance. Okay, so that's the overall embodiment of. And there's some things that are surprising, and there are things that are that are sort of obvious. Okay. Let's get started. Okay, so chapter 4, beginning of chapter 4. Now, I probably should have done this. I probably should have done this slide much earlier, but there are so many acronyms out there. And, I guess you open up Google and you Google it to see what it means. Okay, this is where I got to open up the other one, because I got in my notes, I got them listed out what things are. Just so that I get it right. Okay, IoT, information theory. All right. So examples of the wide area network are the cell phone, the GSM. Okay. Now you're talking miles, and the 2G, 3G, 4G, 5G. Those are all wireless wide area networks. The wireless local area networks is going to be our Wi-Fi. Okay, so this will be 802.11. And again, we'll have an example of that. The personal area network is personal, means yours, right? And that's our Bluetooth. As an example, it's not the only one, but Bluetooth is a personal area network. Now, then you got a whole bunch of things that I've actually never heard before, and that's the home area network and the field area network. I guess that's a personal area network in your house. Okay, it's a home area network, or a field area network is, I don't know, your personal area network on the farm. Okay, this was kind of cool. That's vehicle to vehicle, and that is, can you get trucks and such to communicate with each other while they're moving. Okay, and so we'll see where that fits. And then the low power wide area networks, that's the long range network, like LoRa and Sig. We'll see it on actually Sigfox. Yeah, Sigfox. Yeah. We'll see the next slide. And again, we're going to cover these later. And then regional, I don't know. Again, I never. I don't. It's basically in the TV range. It's in it uses the TV spectrum, and it's longer range. You'll see in the next slide. Okay, so the idea of this is just because it has wireless is not the same, right? There's lots of things that matter, and cost, power, bandwidth, distance, reliability, security, all the things that matter will be all different for these. And this was a fun plot. This is again out of the book. And again, I wouldn't necessarily take the exact spot for these networks. But, you know, as we, you know, as you try to go faster and further, okay? So you're not surprised to find out that some of these things, okay, to go very far, have to go very slow, okay? So those are the long range protocols that go multiple kilometers, but in bits per second, right? And not necessarily in millions of bits per second. But the Bluetooth fits in this short range, moderate speed, and the Wi-Fi's, these are all the 802.11s, the Wi-Fi's are short range, higher bandwidth, okay? The vehicle to vehicle is a little bit longer range, so you can keep track of your, you know, you can have the vehicles talk with each other over longer range, but at a lower rate. Okay, where's the other ones in here? And these are the cellular, protocols, right? The LTE, the 5G, that kind of. So it's an interesting plot. Yeah, again, RFID, I'm not sure it goes 10 meters. Okay, I don't know, you can go that far. Oh, here it is. Never mind. Okay. Yeah, now you're on another centimeter. And the RFID is the passive one. The near field communication is the bidirectional active one. Okay, where you're dumping power. And go a little bit faster. Okay. But again, very short range. Very, very short range. And here's some equations. Before I get to this one, okay, let me make myself a slide and see. Let me make myself a slide here and ask you the general question. New slide. Okay. Why is received power not R cubed? If you were to radiate a field, right? If you were to radiate a field, if you have a dipole, why would the field not radiate in all three dimensions? You saw a glimpse of the next slide. It is R squared. But why is it not R cubed? If you took a radiative source and you dumped energy into the air, and you had a three-dimensional space, and you looked at the corresponding, triple integral of this energy as opposed in this little voxel, why would that not be the amount of volume, right? The amount of volume in this space is R cubed.
That have something to do with aperture or the directionality of the antenna?
Yeah, it's clearly directional, right? It's clearly it's not radiating in all three dimensions. Okay. It's radiating in two dimensions. But as you know, your phone works regardless of where it's oriented. So there's something else going on that's making it two-dimensional. Because it turns out all the equations that I've seen are either you know, or two arc squared or r. Okay. You know, that's an interesting thought question. So it's either directional or what's the other thing that's forcing it to be planar? As we're on the surface of the Earth. Okay. So anyway, I do believe that's probably the reason why it's two-dimensional and not three-dimensional. Okay. Although I'm not quite sure. It's just an interesting thought exercise. So the equations get more and more complicated. Oops. Oh yeah, before we get, okay, did I go? Okay, here we go. I actually got these out of order. No, this one's fine. No, this is a good spot. Okay. So in the context, again, this is a picture, this is an equation out of the book. And you have a transmitting power. This is the amount of power you dump into the antenna when you're transmitting. This is the receive power. I don't know why they showed it bigger, but it's probably not usually bigger, it's usually less. But P sub R is the receive power.
I thought the R was for the inverse power law, just of electromagnetic waves, and the
okay.
addressing is just for the aperture.
Okay. Again, the simplest formula for the received power is an R squared distance. An R squared distance between the two antennas and a wavelength dependence. This is the wavelength of the light. This is the gain this is the gain of the transmitting antenna. This is the gain of the receiving antenna. And 4 pi r squared is obviously a planar dimension. And okay, so okay, before we go any further, we want to put units to things. Okay, so if I said the receive power, what units might you put for that? Watts. If transmit power also in watt. If I said the transmitter gain, what units are in the transmitter gain?
Dimensionless.
Yeah, this is unitless. And then what about R?
Meters.
Yeah, meters, centimeters, inches, furlong, you know, furlongs. And then the wavelength would also have to be in that same unit. So again, and so once you've got units on this, then you can sort of understand the equation down on this second equation right on the same page. Has got all the same terms in it, but it doesn't have, you know, it's got adding rather than multiplying. Okay. And so there's something fundamentally, okay, with some decimals. Okay? So this is in decibel form, okay? And this guy, I don't know if he didn't take calculus or something, but before you get going, what are the units of each of these terms? These are in decibels, okay? And so how do I get from this equation to that equation? this is not the same PR. That's the point of this. If we call this PR prime, okay, PR prime is 10 log base 10 of PT, PR, but that's not correct. You can't do 10, sorry, 10 log 10. But you can't, this doesn't make any sense. Because you can't take a logarithm of something which has got units of watts. So what he actually, in order to derive this equation, you have to go PR minus PT prime is equal to 10 log base 10 of PR divided by PT, okay? So if you make this definition of PR, so you got the change in power, then you can go through and derive this equation from that equation. Okay. This one's fairly easy because this GI again doesn't equal that one. These are all somehow, those are the same, but these are not the same. This again, this gain is unitless. This one's in decibels, but you can do a GTX prime equals 10 log 10 log 10 of GTX. Okay. So basically you go through this equation, move the PT over there, and then multiply everything by 10 log base 10 of GT, right? So you take this equation, first write it PR divided by PT, okay, equals this. And then you take 10 log base 10 of both sides. And then you get this equation. All right, where'd the 20 come from? If I take 10 times log base 10 of both sides of this equation.
Oh yeah, it's the decimal part.
Where'd the 20 come from?
The squared. The squared.
Yeah, the 2. You saw the 2 is gone here. The takeaway here, I guess, is wavelength is important. All right, and so if I want more received power, what do I do with the wavelength?
Make it bigger.
Yeah, and how do I make it bigger? I make the frequency smaller, right? So you'll see that these guys have a lower frequency than those guys, right? So this is a lower frequency carrier. All right. Okay. So now it gets a little fun, and this is where I just want to remind you that when you're doing wireless stuff, don't just look at the frequency. Have a physical intuition about its wavelength. Because the reason that X-rays are dangerous is because the wavelength of an X-ray is on the order of the atoms, and therefore atoms can be split, destroyed with X-rays, right? So ultraviolet light is dangerous because it can split molecules, okay? Visible light is not dangerous because it's it doesn't, I mean, you can make things hot, but you can't, you're not going to destroy anything. Nothing about human life is going to be destroyed with wavelengths in this dimension because the wavelength is larger than the structures that are vulnerable. Okay. And so we're in this gigahertz microwave range, and the wavelengths are on the order of 10 centimeters or 30 centimeters and that kind of wavelength, which means when you ask the question, if a light hits an object, what will it do? Will it reflect? Will it refract, which means it changes frequency, right? It bends twice and changes frequency. Will it get absorbed, right? Or would it get scattered or diffracted? Okay, I'm sorry, refracted. Diffraction is where it changes frequency. But what will it, then it's a matter of the size of this wavelength to the size of that object. And so, you know, that's what's going to answer our question of, does it go through a concrete wall, right? And then scattering is where the light goes in, the energy goes in all directions, and it's no longer directional. So the point of this is to think about the wavelength when you figure out what's happening here. Okay, so now the formulas are getting more complicated. This is the equation from before, the first equation. And this is that same equation shown in, what time is it? Okay, almost done. Almost done with my time. In sort of general terms, you put in power, the antennas may cause the power to increase, and then any losses, and this is the free space loss, the loss in free space as a function of wavelength and distance, okay? This guy again didn't, this equation makes sense to me. This is the free space loss. And all they did was take this minus sign here and take that minus sign there. And then, yeah, and then this equation makes sense to me because all he did was flip the minus sign and flip the order. This one makes sense to me, that he just, you know, took the, you know, wavelength equals C over F. Wavelength equals C over F. Okay. But this one makes no sense to me. I copied and pasted it there just to make fun of them. You can't do this. Why can't you do this?
Dimensions?
Yeah, I mean, you can't take the log of something that has meters, okay? You can't take the log of something that has hertz. You know, I think his heart in the right place. It says the same thing we said earlier, and that is lower frequency goes further, okay? That's a, you know, this equation here says if I drop the frequency, it'll go further, okay? I'll have, you know, I'll have less loss. All right, it's 10:44. Okay, I'm going to read myself a note this time so I can, when we, all right, so discard. Okay, so this is where I ended, star. All right, I'll upload this. Okay, share, stop sharing, save. Okay, upload. All right, questions? Yeah, how we doing? Yeah, so now we're into the wireless part. We'll do the Shannon channel capacity theorem next time. Okay, IoT, upload. I'll go ahead and upload both the other one because it had a website and it had a thing in it. Okay, that one. Upload. Technology. Okay, questions? I think what I'm going to do is we're 3 weeks into the class. I'm going to post up on Canvas an anonymous survey. If you want to say something unanonymous, just say it to my face. But if you want to feedback how we're doing, what's going well, what's going poorly, before I get to the end of the semester, that's the purpose of this. So it's going to be a short, it'll be a short survey, what's going well and what's going poorly. And yeah, I don't know if you, has anybody bought the book? Okay, raise your hand or speak up. Is the book, yeah, Caleb?
Yeah, I have. Okay,
Austin. Corey. Yeah. So those of you that have bought, yeah, all of you. Okay, most of you. Okay. What do you think of the book? Okay, maybe 3 questions. Yeah. So, and don't worry about to answer that question, read the section in chapter 4 that we just did today, right? Because the purpose is for the book is not to be an embedded system book, but to be a communication wireless book. Okay, so look at chapter 4 or 5 or 6 while you evaluate what you think of the book. I liked it because it had a lot of equations in it. It's just I love my equations, so, even though I don't particularly like all the equations. Any questions? All right, I'm 12 days away from the exam. It's going to be an open notes exam. It'll have, things to think about, equations to derive, basic design. I'll give you a study guide. Anyway, take care and be safe out there, okay?